Hey everyone, welcome to my channel. In this video we will learn how to create an image classifier using feature detection. We will first look at the basic code of feature detection and description, and then we will move on to the classifier project. I upload videos on a weekly basis, so don't forget to subscribe and hit that like button if you find this video useful. So let's get started. So here we are in PyCharm and we have our main directory, and you can see here we have images query and images train folder, and what we have inside are 3 images of each, and you can see that we have covers of games. So the idea here is to detect these games, and what we are going to detect in is our train image. So we will try to find our query image in this given image, which we will call as train. So the first thing we will do, and you can see there is another image outside for Assassin's Creed. I will explain why that is later on. Now the first thing we will do is to import our libraries. We'll go to File, Settings, and our project interpreter, and we are going to import OpenCV and NumPy. OpenCV Python and NumPy. So once we are done, we are going to import our libraries. So import cv2 and import numpy as np. Now the very first thing we have to do is to grab our images. So we are going to use the imread function. So image1 is equals to cv2.imread, and we are going to grab our query image. So we will say inside images query we have, which one should we pick? Let's pick the Xbox. So Xbox Kinect Sports, and then image2 is equals to cv2.imread, and then we will write train image, and inside we will grab, what is the name of it? It is Kinect. So now we can test it out if it's working. So we will write cv2.imshow, and we will say image1 and image1, and then cv2.imshow image2 and image2, and then we can write cv2.waitKey, and we will give it 0. So if we run this, and here you can see we have our 2 images, image1 which is our query image, and image2 which is our train image. So next we are going to create our detector. Now the detector we are going to use is known as ORB, which is oriented fast and rotated brief. So the idea here is to find features. So what are features? So let's have a look at the OpenCV example. So this is given in their documentation. So here they are explaining the features, and we can see that we have a building, and they have shown A, B, C, D, and E, F. So if these are the features, how easily can a human being detect these features? So if I were to ask you how to find A, you will say that A could be anywhere here, and B could be anywhere on the right hand side of the building here. If you look at C and D, they are over here. So these are the side rails of your building. But if you look at E and F, you can pinpoint the exact location of them. So E is your corner point over here and F is your corner point over here. So we can say that E and F could be considered good features, whereas A and B or C or D not so much. So A and B are the worst ones, C and D are better, and E and F are the best ones. So the idea is to find these features, and once we find these features, we are going to translate them into computer language. So that part we will call as descriptor. So when we translate our feature to computer language, that will be a descriptor. And then using those descriptors, we will match two different images. So if it's a little bit confusing, don't worry, we will go ahead and explain this step by step as we go along. So for feature detection, ORB uses the FAST algorithm. So actually a modified version of FAST, which is oriented FAST. So let's initialize our detector. So we will write ORB is equals to cv2 dot orb underscore create. Now you might be asking, why are we using ORB? Why not other algorithms? There are some common ones like Swift or Surf. Well, ORB is one of the fast ones and the one that is actually free to use. If you use Swift or Surf, you will have to pay yearly fees because they have patents. So now we will find our key points, which are our features and the descriptors for both images. So let's write down KP1 as our key points, and we will write DS1 as descriptors is equals to orb.detect and compute. And inside we are going to write image1 and none for the mask. So the same thing we can do for the second one, and we can write here 2 and we can write here 2 and 2. So in order to understand these, let's print it out. Let's show these key points. So what we can do is we can use the built-in function for drawing key points. So we will say image kp1 key points 1 is equals to image is equals to cv2 dot draw key points, and we will send in our image1 and we will send in our key points kp1 and we will write out image as none. Now one thing we did not do so far, actually let's do it for the other one as well. Let's paste that and 2 and 2 cv2 dot imshow, and we will write kp1 and this will be image kp1, and we can copy this and we will write here 2 and 2. So one thing that we did not do before that we should is to import the images in grayscale. So that will ease our process. So we can just write here comma and 0. That will import it as grayscale. So let's run this. So this is our image. Yeah, so here we have our images now with the key points shown. So all these key points are the ones that the algorithm has found to be useful. So you can see here where it says season 2, you can find similar key points over here. Right next to the Kinect icon, you can see that we have similar key points. Now we have these features now, but we need to describe them, and that's why we have our descriptors. Now what are these descriptors? These descriptors are basically an array, or you can say they are a bin of numbers. So if we print them out, let's see. So if we write print descriptor 1, And if we run this, you can see it's just a bunch of numbers, but let's see what is the shape of it. So if we run this, we can see the shape is 500 by 32. Now that looks like an odd number, like what is 500 and what is 32? Now the idea here is that the Orb detector uses by default 500 features, so it will try to find 500 features in your image, and for each feature it will describe it in 32 values. So if we look at descriptor 1, let's print that out. So you can see that it's 32 numbers put together in an array. So this is one descriptor, so we have 500 of these for each image. So how can we use these descriptors now? So what we can do is we can use a matcher to actually match these descriptors together. So I have the descriptor of image 1 and I have the descriptors of image 2, and I can match these two together and see how much similarity am I getting. So we have different types of matchers as well. Now one of the most common ones is the brute force matcher. So basically it takes one descriptor and it matches to all of the other descriptors of the other image. Then it goes to the second one and it matches all the descriptors of the second image with our new descriptor. So this process is very computationally expensive. So there's another technique of the brute force which uses the k-nearest approach, k-nearest neighbors. So we are going to use that instead. So let's have a look at that. So what we will do, should we remove this or let's keep it? Let's keep that there. And over here we are going to write our matcher. So we will say that our brute force matcher is equals to cv2 dot brute force matcher, and we are going to say that matches is equals to brute force dot knn match, and then we are going to send our descriptor 1 and we are going to send our descriptor 2, and we are going to give our k value as 2 because we want two values that we can compare later on. So this will give us our matches. But how do we decide that which is a good match? So what we can do is we can go through all the matches and we can find the distance between two matches and the two features, and then we can decide if that is a good match or not. So we can write here good is equals to an empty list, and for m and n in matches, so because we said k is equals to 2, we will have two values that we can unpack. So we are going to say that if m dot distance is less than 0.75 multiplied by n dot distance, then we are going to append and we will decide that this is a good match. So we will say good dot append and we are going to write in between m. So whenever the distance is low, the distance between them is low, we are going to say that it is a good match. If the distance between them is high, we are going to say that it's a bad match. So you can change the value over here based on the results you are getting. 0.7, 0.75 is a good approximation. So now that we have all our good matches, what we can do is we can plot them out to see what we are getting. So we can write image 3 is equals to cv2 dot draw matches k and n, and we will write image 1, then kp1, then image2, then kp2, and then we will write, we need to give the good matches, and then we will write here out image to be none. And for the flag is how do you want to show, so we are going to write it as 2. So let's output image3. So if we run this, and there we have it. So now we can see that it's showing us where did it find the appropriate matches. So you can see that here it's by the end of the racket, here it's by the end of the racket, here you can see it's found this to be here, which is wrong. Then you can see the S over here is detected here. So there are some good matches, and then there are some bad ones. So we can change the value to actually fit these. Also, what we can do is we can increase the number of features it has to find. So we can write n features is equals to, by default it's 500. We can put, for example, 1000. So let's run that again, and you can see now we have much more matches. So what we can do is we can actually print out the length of our good matches, so we know that how many good matches we are getting. So we can write print length of good, and if we run that, we are getting 42. So we are getting 42 good matches. Now if we were to do this for another image, so right now we are using the Kinect image, which is this one, which has the actual image. But what if we used another image, for example this one? Let's see how many matches do we get there. So our image 2 this time will be the other one. So let's comment this out, and if we rerun this, and there you have it. So now it did find some matches, but you can see that the matches we found are only 5. So earlier we got 42 matches, and now we are only getting 5 matches. So we can clearly say that this is not a good match. This image, our query image, is not present in our train image just by looking at the length of our good list. We can also do it with the other one. Let's write that down last, and let's rerun it. And there we have it. So again, we are getting very low numbers. We are getting 7. So again, we can tell that this is not a good match because the number of good matches are very low. So next we are going to create a project out of this. So what we will do is we will create an image classifier in which we have these 3 images, our query images, and whatever image we feed in, we are going to find out which of these 3 classes it belongs to. So this means that let's make it in a way that it is generic, so that whatever number of images we put here, it will automatically create that number of classes and run the code for us. So let's create a new file first. So we'll go to Python, and here we will create image classifier using feature detectors. So let's just copy our original code. We will copy this and we will paste it here. Now the very first thing we should do is to let's import our images. Now we can import our images one by one, so image 1, image 2, image 3, but that is not a good way to do this. And as we mentioned before, we want to make a generic code in which it will automatically detect how many images are inside our folder, and it will create that many classes. So in order to do that, we need to use OS. So we will import import OS, and then we are going to find how many images are here, and we will store the name of all these images so that we can import them. So let's comment all of this out, and over here we are going to write first of all our path. So our path is basically the image query, and what we will do is we will create two lists in which we will store all our images, and the second list we will store all the names. So the names will be PS4 Detroit, PS4 The Last of Us, and Xbox Kinect Sports. So the reason we are storing the name so that we can display whenever the class is detected, we can display the name of the class instead of just the ID. So we will create a list called images is equals to empty, and class names is equals to empty. Then we are going to find the list of the names that we have in our path, which is images query. So we will use my list is equals to os dot list directory, and we will give it our path. So if we print this out, print our my list, and let's see, it is running the previous code. Right click and run, and there you go. So now you can see that we have a list of names of our images which we can use to import. So here we can write, or should we write, let's write print, and we will write total classes detected, and over here we are going to write the length of my list. So whenever we run it, it will first tell us how many images it detected, how many classes there will be. So if we run that, it will say total classes detected is 3, and we know that we have 3 images, so we are good to go. Okay, so next we can import our images. So we know that we are using imread function to import, but we have to give it a loop to actually go one by one and import. So then we can say that for class in my list, we are going to import. So we are going to say that our current image, let's write img current is equals to cv2.imread. Now we have to put in our path. Our path is basically, so let's write our path, then we will have a slash, and then we will have the name of our image with the extension, which is basically CL. So we can write that, and as you know, we are importing it in grayscale, so we will write 0. Once we have imported that, we will append it in images. So images dot append, we will append our current image, and then we are also going to append the name. So we will write here class names dot append, and we cannot append CL directly. Let me show you why. So if I print CL, you will see that it contains the extension as well, .jpg. So when we are displaying the name, we don't need to display .jpg. So we need to remove that. So in order to remove it, we can write os.path.split text, and then we are going to write here CL and 0. So now it will be stored without the file extension. So we can print it out and see if it works. So we can print class names, and there you go. So now we have the names without the extension. And we have our list of images. What is wrong with the spellings? Images. So the next thing will be to find all the descriptors of our given image. Now all of this, these descriptors we only have to find once, because these are constants, and the image we will get from the webcam, we will find the descriptor for it when we get it. So all of this we can do outside the while loop. So what we can do is we can create a simple function that will take the list of your images, and then one by one it will create the descriptors and it will store it in a new list. So let's write that function. So we will say, let's say find descriptor, and we will send it our images. So images, and then we will first declare our list. So this will be our descriptor list, and then we are going to loop through all the images that we have. So we will say that for image in images, we are going to find the key points and the descriptor for it using orb.detect and compute, and we are going to send image and then none. Now it says orb is missing, so we have to uncomment this. So all of this code is basically to import images. So this whole code is for importing, and so now we have the orb, and once we have that, we can append our descriptor in the descriptor list. So we can write des.list.append, and we will write our descriptor, and at the end we are simply going to return our descriptor list. Now all we need to do is to call this function. So we can call it simply by saying descriptor list is equals to find descriptors, and we will send our images. So that should do it. So if we print the descriptor list length, then that should give us 3, because we have 3 images, and there you go. So it gives us 3. So it means it's storing all the descriptors of each image properly. So the next thing we need to do is to now define our while loop. So let's remove some of the code from here. So this part we have already done, which is importing the images. Then we do not need to draw the key points, and we have done the detection part. So let's remove that, and we have to define the matcher and this still. So we will keep that. So now let's write down the code for our while loop. So we will say while true, we are going to get the camera feed, and for the camera we have to write cap is equals to cv2 dot video capture, and we are going to use device number 0. Here we will write success, and image is equals to cap dot read. And now that we have the image, we are going to convert it into grayscale. Actually, let's copy it, because we want to see the colored image at the final output. So we will say image original is equals to img2 dot copy. So let's put this as image2, and then we can simply convert it. So image2 is equals to cv2 dot cvt color, and then we will write image2, and we will write cv2 dot color bgr2 gray. So this will convert it into grayscale, and then we can write CV2. Let's copy one of these. Oh, we have it already, so let's write this here, and we can also copy the wait key, and we will put this as ones because we want 1 millisecond. So if we run this, and there you have my webcam, and you can see we have all these games that we are going to test. So as I mentioned before, we want to see the final output as colored, so we will use image original instead of image 2. So now you can see we have the colored images. Okay, so now we have found the descriptors of our Curie images, but we did not find the descriptor of our webcam image, so the one that is coming from our webcam. So we need to find the descriptor of that, and once we have that, then we can use our matching algorithm to find the difference between the both descriptors. So let's create a new function for that. Let's call it find ID. So the idea here is that we are going to send in our image, and we will send in the descriptors. So inside the function, we will find the new descriptor of our current frame, and then we will match all the descriptors, and at the end we are going to send in one single ID that it matches the most with. So our return value should be just a single number, for example 0, 1 or 2. So if it's matching with Detroit, it should be 0. If it's matching with Last of Us, it should be 1, and then 2 for Xbox Kinect. So let's write that down. So we will write find ID, and we will send in, as I mentioned, we are going to send in two things. We will send in our image, and we will send in our list of our descriptors. So the first thing we will do is we will find the descriptor of our new image. So we will say kp2, and our descriptor 2 is equals to orb dot detect and compute, detects and compute, and inside we are going to write image and none. So once we have that, we are going to use our previous code to find the matches. So over here you can see that we are using this, so we will copy this. Let's just comment this out, and then we will copy this and we will paste it here. So now we can remove that. So now you can see that we have the descriptor 2, which is good, which is our descriptor of the current frame. But what is the descriptor 1? Now the descriptor 1, we don't have just a single value, we have multiples of them. So we have 3 different descriptors that we want to compare with. So we cannot write descriptor 1 here. So what we can do is we can loop through all the descriptors and match them one by one. So here we are going to write for descriptor in descriptor list, we are going to match. So we are going to match our descriptor, the current descriptor that we have. And then inside we are going to apply our same method that we did before to find the good matches. So we will copy, we will cut this, and we will paste, where is it? We will paste it here. And this time we are going to find again the good matches, and we will find the length of our good matches, and then we will put it in a new list. So what we will do is we will declare a new list. We will call it match list is equals to empty, and instead of printing it out, we will just append it, match list dot append This way it will append the number of good matches it is finding for each of these images, and it will give us an output list. So let me just print it out so that you can understand it better. So print match list. But we didn't call this function, so it will not work. So let's call it over here. So we can say find ID, or is ID find? What is it called? Oh, it should be D, find ID. Find ID, and then we will send in our image 2 and the descriptor list. And let me run that. And there you go. So now you are seeing a list which is our match list, and what these values are is basically the number of good matches it is finding for each of these QD images. So it's saying that it found 10 matches with the Detroit image, it found 27 matches with The Last of Us, and it found 7 matches with the Kinect sports game. So as you can see, the image we were looking at was actually The Last of Us. So this means it is pretty much correct, because the most matches, the most good matches we are finding are for The Last of Us. So what we want to do next is to find the maximum value, and then we just want to send out the index. So here the maximum value is 38. So we will send the index 0 and 1. So we will send the index of 1. So in our final image, we can write the name of image 1, which will be The Last of Us. So how can we do that? We can define here a new variable by the name final value, and we can put an initial value of -1. We cannot put 0 because 0 is also a value. So 0 will be Detroit. So this is 0, 1 and 2. So we will initially put -1, and then what we will do is we will find the maximum value. But before we do that, we need to set out a initial threshold, the minimum threshold that it should have at least, for example, 10 good matches or 15 good matches to qualify it as an actual match. Otherwise, if nothing is available, it will just randomly keep matching, which will not be accurate. So in this case, we can see that we are getting 12, we are getting 4, we are getting 6, 7. So most of the time, if the value we are getting the good matches is less than 15, if it's not the actual match. So here it's 12 again. So here 13, 12, 13, and pretty much that's it. So we can say that if it's above 15, it means it is a good match and we need to consider it. Otherwise, we will not consider that value at all. So let's do that. So we will remove our print, and down here we are going to write, first of all, we will check whether it's empty list or not, because sometimes you might not find any matches and it might give you an error or something. Actually, that reminds me, we should put here a try and exception as well, because sometimes the matcher does not match anything and it gives out an error. So we can write here try, and over here we can write except pass. So all of this should be inside the try. Okay, then let's write down here. So here we are going to write down, first of all, we will check whether our list is empty or not. So we will say that if length of match list is not equals to 0, then we are going to check if our max value of our match list, so this max value will be For example, 32 in this case, 28 in this case, 20 in this case, and so on. So if that value is greater than let's say a threshold, so that threshold we can ask the user to define. Actually, by default we can put 15, and if the user wants to, they can define. So if the maximum of it is greater than 15, then we are going to find the index of it. So we will write final value is equals to match list dot index of max of our match list. So this here will find the maximum value, which is let's say 32, and this here will find the index of it, which is 1. So 0 and then 1, and then we are sending it to final value. So final value was -1, it will become 1, and then we will return this value. So we are always going to return, so return final value. Okay, so that is pretty much it. Now what we can do is we can save our final value. So we can say that id is equals to find the value, and do we need to define the threshold? Well, let's not define the threshold, and then we will just check that if id is not equals to -1. If it's -1, we will not print out anything, but if it's an actual index, then we will write down the name of our class. So here we will say cv2 dot put text, and we will put it on the image original, and then we will write our id. So here we can write id, but writing the id will not give us the name, so it will not be very clear. This is why we had this class names. So what we can do is we can say that find the index at the id given. So that will give us the name, and because it's already string, we do not need to convert it, and we can place it like 50-50, and then we have to give it a font, cv2 dot font. Let's pick any font. Then we will give it a scale, and then color we will give it, let's say, red, so 00255, and thickness, let's give it 1. So let's run that and see what happens. So there we have, and if I put it like this, so it says The Last of Us. Actually the thickness is a little bit thin, let me increase that. So here we have PS4 The Last of Us. This one is not defined, so Xbox Kinect Sports and PS4 Detroit. Now you remember that I mentioned in the beginning that this one was not defined, and if I don't put any of these, you can see it does not show anything here. So this means that our function here, this maximum threshold part, is working properly. So as you remember, I mentioned that this image we are keeping outside the folder of our image query. Now the reason I put it outside is because I wanted to show you how easy is it to add a class. So if I just drag this image inside our query images folder, now if I run it, you will see that it will not display 3, it will display 4 classes, and it will be able to find the Assassin's Creed as well. So if we run that, you can see already here it says 4, and you do not need to worry about their order. It will automatically detect and place it in the correct order. So if we go here, it still says Detroit, and if we go to Assassin's Creed, and now it's saying Assassin's Creed, and you have Detroit, then you have Xbox Kinect, and then you have The Last of Us. So this is how you can create a simple project with feature detectors which can classify your images. Now you do have some limitations on this. Mostly the images you are trying to find should be 2D, they should not be a 3D object, and most of the time it should have good texture. So the more texture it has, the better features it will be able to extract, the better descriptors we will get, and the better matching that we will get at the end. So this is it for today's video. I hope you have learned something new. If you enjoyed the video, if you found it useful, give it a thumbs up, and I will see you in the next video.